Welcome back. So today we are going to start with the introduction to the phasors. As you know, the circuits that we use in our everyday life, the electricity supply that we are having is a single phase or a three phase supply in which the voltage and the currents are uh, they are sinusoidal in nature. If you recall that they are sinusoids, and let me just complete this figure 1 minute. Yeah. So what we have typically can be described by what we see every day in our life can be described by such RLC circuits. So, so what we are having here, uh, actually, but there is a switch also, but that's okay. We could think of a sinusoidal source described by Vm of sine of omega t plus phi, where omega is 2 pi f, f is the frequency, 50 hertz in our country, India, 60 hertz in North America, 50 hertz also in Europe. So, so the waveform is, if you look at the waveform, it's a sinusoidal voltage waveform like this. Um, so, and it goes on and on and on and on. So this is my uh, Vm, and at omega t equal to, suppose this is omega t, at omega t equal to minus phi, it becomes 0. So therefore this is the minus phi angle which is here, and at pi by 2 minus of phi, at an angle of pi by 2 minus of phi, it will reach its peak value of it will reach its peak value of what is it, the peak value of Vm, and then will come back to 0 at 180 degrees, or pi radians minus phi, and then you will get the negative lobe and so on and so forth. So if the phi is set to uh, if the phi is at 0, you will get your regular uh, you will get your regular Vm sine of omega t, and if the phi is set to minus pi by 2, if phi is set to minus pi by 2, then you will get it as Vm cos of omega of t. Sorry, if the phi is set to plus pi by 2, then you will get it as uh, Vm cos of omega t, and so on. So Vm cos of omega t is going to be, I'll just put this here, waveform which will look like, you can complete it, the remaining part, a waveform which will look like this, and a sine of omega t is a waveform which will start like this and will become 180 degrees here, and then it will go like this. Okay. Now, in our circuits, we will have, in AC circuits, we will have sinusoidal voltage or current source, typically voltage source. Any dissipative element is shown by the resistance, and anything which is related to stored magnetic field energy is shown by inductance, and anything which is related to storage of charge is shown by capacitor. So that's why RLC is a good circuit representation, and you could, though series RLC is enough for us to start with, you could also have parallel combination of the series RLC circuit. So you could still have a circuit which is a parallel combination of Vm sine of omega t plus phi. Now, why sinusoids? Okay, so why sinusoids? So I like to connect it like this. Maybe I have also mentioned it earlier also in my class, but let me repeat it repeat it again. Any number of times you differentiate or integrate a sinusoid, you get a sinusoid. And by sinusoid, I also mean cosinusoid or cosine. That co means it's just the brother or sister of the same waveform. Really, the shape of sine theta and cos theta is the same. It's only where you put your reference line theta equal to 0 that alters its description as whether it is called a sine theta or a cos theta. So shape wise, it's essentially the same. And this helps us a lot, because this basically means that the signal does not really alter except for scale and phase shift as it transmits through wires and RLC elements. This implies that the signal shape does not change. This is important. For example, if suppose I voltage across an inductor, okay, so it is L di by dt. Now let's say that Im is equal to Im sine of omega t, the sinusoid. Now what happens to V of t when you substitute it here? It becomes omega L Im cos of omega of t. So the signal has this signal has scaled by this signal has scaled by omega L, which I call as reactance, inductive reactance. I'll connect it later on again, but this is called as inductive reactance, which is the scaling factor of omega L, and the signal is scaled by that value and has phase shifted by 90 degrees because the sinusoidal has become cosinusoidal. So other than that, actually it's still a sinusoidal waveform, which is therefore, as I said, uh, uh, which is just scaled and phase shifted. So as it transmits through the wires RLC elements, the signal shape does not change. You just have scaling and phase shifting. Similar behavior you can see that if the current across the capacitor is given by C dV by dt, and if Vt is taken to be equal to Vm of sine of omega of t, then I of t will become equal to omega C Vm cos of omega of t. Is it not? So omega C Vm by cos of omega of t. So in this case, this so I called this as inductive reactance because of the analogy that V of t is equal to R of IT. This is for a resistive circuit. So here V of t, though phase shifted, but so it's I of t plus 90 degrees, but otherwise this is the current, this is the voltage, and so the ratio of the voltage to current should be something similar to resistance, but is not resistance because it is not dissipative. So we called it as reactance and associated with inductor. So therefore, the inductive reactance. Similarly, here, if you look at the ratio of V by I, then that is going to be equal to 1 by omega C. So this will be called as capacitive reactance. So we have two terms now, inductive reactance and capacitive reactance. And what is the if the what is the ratio volts by ampere currents? It always has the will always have the unit of resistance, which is ohms. So therefore, the inductive reactance will have a unit of ohms, and so will capacitive reactance 1 by omega c will also have a unit of ohms. So see, if you integrate a sinusoid also, just if you differentiate, it doesn't change the shape and remains something like a sinusoid only, though phase shifted and scaled. Then when you integrate it also, the reciprocal behavior is there. Therefore, it again it will get altered in, it will be scaled reciprocally. That is, if it becomes omega times here, then it will become 1 by omega times here, and there will be a phase shift as it was earlier, because when you integrate it, you restore back your original signal. Suppose you differentiate and again integrate, you will get the same thing back. So the phase shift will also be in the reciprocal sense, but otherwise it will still remain a sinusoid. So a circuit like this, I am not showing switch here, switch not shown, because right now what I am diving deep into is understanding of steady state performance. So in the steady state performance, we can assume that the switch has been closed for a long amount of time a priori, and now all the transients have settled down, and we are looking at the steady state performance of the circuit. Okay, so just quickly let me write down the differential equation of that circuit. This is equal to V of t. This is the differential equation of a series RLC circuit. The right hand side is our forcing function, which in our case is going to be a sinusoidal voltage source. And this one is basically Kirchhoff's voltage law, VR plus VL plus VC is equal to V of t. The current which is flowing through this loop is I of t. Deliberately here, a dummy variable tau is used for the integration. So if I use the same t, there is certain abuse of notation, which I have just avoided by saying it here. And actually, you could even write this as minus infinity to t. More appropriately, it is correct to write it as minus infinity to t. All right. So, one very important point that I want to make here now is that, just looking at this and wondering about the steady state response, I want to make a let's say a conjecture. Okay, I want to conjecture that sinusoidal response excitation will lead to sinusoidal response. Okay, let's understand this more clearly. One thing is, assume that current was a sinusoid. I always conveniently take one side. The equation can be understood by either assuming RHS or directly assuming the response. So, for example, if I assume that the current is sinusoid, so then R I am sine of omega t. R I am sine of omega t. I of t is taken as I am sine of omega t plus omega L I am cos of omega t by substituting for di by dt plus by integrating it I'll get 1 by omega c and assume this that from minus infinity to 0 uh, from minus infinity to 0 this voltage uh, I of tau d tau 1 by c which is the uh, is which is basically integration of current is charge. So assume that the capacitor was discharged, then the charge was 0, so the corresponding voltage was also 0. So the initial condition, if you suppose close the switch at t equal to 0, then you would know that the initial condition is 0. But and right now I'm not trying to solve the complete circuit. I'm just saying that so I will for the time being ignore these things and just write 1 by omega c and then I of t if it is integrated, sine is integrated, so cosine is differentiated becomes minus sine, so this will become minus cos, so I'll get minus I am cos of omega t to be equal to, let us say, will be equal to v of t. Now, if I group the things together, if I group, so everything, if I group the things together, I can write this as R I m sine of omega t plus omega L minus omega c I m cos of omega t to be equal to Vt. So now what I will do is I'll construct a right angle triangle R. Take this as omega L minus 1 by omega C. I am assuming omega L dominates 1 by omega C, and so omega L minus omega C is positive. It could be negative also, it doesn't matter. It is just a notion of convention. This I'll call it as theta, and this I'll consider it as a right angle triangle. And the hypotenuse is something that I'll use the symbol Z. It is pronounced as impedance. Again, the word, again, its interpretation will be very clear why it is called impedance. And I'll write this as the positive square root of r square plus omega square into 1 minus omega L minus omega C. And therefore, square root of ohm square plus dimensionally square root of ohm square. So, therefore, dimensionally equal to ohms. So, now what I am going to do is I am going to divide this by Z, divide this by Z and multiply this also by Z. So everything remains same. So what happens is now this can be written as Z I m, and for r by Z what can I write? I can write cos of theta and then sine of omega t, and then for omega L minus 1 by omega C by Z, that is perpendicular by hypotenuse, I am going to write it as sine of theta cos of omega of t will be equal to V of t. So therefore, V of t can be written as Zim sin A cos B plus cos A sin B, which is sine of A plus B, which is sine of omega t plus theta plus. plus of theta, where theta is tan theta is omega L minus omega C by R, or theta is written as tan inverse of omega L minus 1 by omega C by R. So now dimensionally, what do you see? You see that first of all, the current which was to begin with was this, has retained its sinusoidal shape but got a phase shift of theta and has scaled by the amplitude z. And if you draw the analogy with V equal to IR, your basic resistive circuit, then dimensionally this Z is also ohm, and it is something similar to resistance. So resistance is already gone. Reactance word has also been taken. So now we have to invent another word which has similar synonym meaning, which is the word which is now invented or used is impedance. So resistance, reactance, impedance, these are synonyms, but resistance physics wise is a dissipative element. It will dissipate power. Reactance will not, because it's only related to storage element, either inductance or capacitance, that is storage of energy in magnetic field or electric field. Impedance, being a combination of RLC in general, will mean that it can also partly dissipate and partly represents a storage element, because it's a combination of R, L and C. So you got Vt equal to sine of uh, Vt equal to Z Im sine of omega t plus phi plus theta. So phase shifted waveform, same voltage kind of waveform, phase shifted by theta and scaled by the impedance. So you are seeing some hints of generalization of Ohm's law for sinusoidal circuits, but so long as we are using time domain interpretation or time domain presentation, it's not very obvious. So therefore, we need to do something on the invention of phasors. We need to do develop our concept or concepts from sinusoids to phasors before we can actually start writing analog of the Ohm's law for more generic circuits like this. Okay. Now I had also drawn the parallel RLC circuit earlier, and so you could similarly analyze the parallel RLC circuit by better to write, though current sources are not directly available in nature as voltage sources are, but I could, for the sake of circuit analysis, I can write this as Im of sine of omega t plus phi, and then these three currents would distribute into IR, IL and IC following the Kirchhoff's current law, and this could be written as, if this potential is V of t is the potential here, then we could write this as V of t by R, and the current in the capacitor would be C dV by dt, and here the the voltage across the voltage across the current across the inductor would be given by dV by dt. So this is what this is the kind of circuit representation that you would get here. Remember, V equal to L di by dt. So if I want to write I as a function of v, then first I have to divide it by L, then do dt. This will give me integral, and then do a integral. So that's why this term here comes for in this case like this. So in the series RLC circuit, if you recall, the capacitive term had come with the integral term. Here the inductor term has come with the integral term. In general, circuits like this, which have both differentials and integrals, are called as integro-differential equations. And if you differentiate it one more time, you can convert it into a pure differential equation. But right now my emphasis is not on solving these differential equations. Solving the complete differential equation will be, the differential equation is important, no doubt, when we want to get the complete response of the circuit when the switch is closed. But I am more interested in actually steady state response. In general, when you apply, you have a differential equation, a set of differential equations here, and you apply a forcing function here, then the response can be thought of as natural response and forced response. So usually this natural response will die down with time due to dissipative nature of R. For example, if I have a RL circuit like this, okay, and uh, and let us say that uh, initially, okay, 1 minute, yeah, so I put the switch like this, a two-way switch. So there are the switch is like a two-way throwing kind of a switch. Initially at t equal to 0, at t equal to minus infinity, means very long time back, I had threw the switch in this position S1, and so some circuit had some current had set up in this circuit. So let's say that to keep my life simple, let me make this as a uh, voltage source, so the a DC voltage source. So a current had set up in this circuit here in the steady state. Some current was, so at t equal to 0, when I am going to move this switch here at t equal to 0, I move the switch here, and now there is no voltage source. So let's look at this initially, this circuit, okay. uh, this circuit, so is equal to V in the from minus infinity to t to 0 in this time, so it's a long time. So the steady state, if a steady state was feasible, then with DC, what would you expect for the value of di by dt in steady state? This value will go to 0. So therefore, the currents will become, in the current become constant in the inductor, then the di by dt will be 0. So the voltage across the inductor will be 0, and so I will be equal to V by R. So the inductance will not create any opposition in steady state to passage of current, to passage of DC current. Only the resistance will create an opposition and you will get I equal to VI by R. So V by R. So let's say this is some 5 amperes or whatever, some value is there. And then I throw the switch at t equal to 0 to this position instantaneously. So without any time lag or delay or like that. So then post t greater than 0 or greater than or equal to 0, I'll write it t greater than 0. My equations will now become, the differential equation will change to plus of IR equal to 0. So the response to this, when the right hand side is 0, the response to this is called as the natural response. And this you have seen it earlier also. I am sure that you have done that earlier. So di by dt is equal to minus of IR. So you get 1 by I di is equal to 1 by R minus of R by L minus of R by L dt, and then you integrate this and you keep the initial condition. So I'm going to leave it to you to do that, solving yourself. Then this will become t by, the response will be given by I of t is equal to a e to the power minus t by tau, where this tau is called the time constant, which in this case is the ratio of L by R. So the ratio of L by R. So at t equal to 0 or 0 plus, if to be more precise, means once the switch has moved, then the current in the inductor cannot change instantaneously. Why can't current in the inductor change instantaneously? Because if the current in the inductor changes instantaneously, then the voltage across this term will go to infinity. So the voltage across the inductor will go to infinity, which is not feasible in a in a physical circuit. So therefore the current in the inductor cannot change instantaneously. So you will have the condition IL 0 minus is equal to IL of 0 plus, which will remain equal to 5 amperes. And so the current in the circuit, in this circuit, will decay exponentially down to I going to infinity. This current will go to 0 amperes. It will decay exponentially, it will decay down from 5 amperes and go to 0 amperes. Typically after 5 time constants there would be nothing left, as good as it would have hit the 0. So the point is that the natural response will cause, the natural response would be such so that its effect after some 5 time constants or something will just vanish. So when we are doing the steady state analysis, we assume that the effect of natural response has gone away. But if you want to analyze the circuit in the first 5 time constants or so, you cannot ignore the effect of natural response. But if you want to analyze the circuit from a steady state performance perspective, because we are only dealing with sinusoids right now, so then the effect of natural response or the initial conditions can be ignored. So in other words, you could think of in this differential equation that I wrote somewhere here, in this differential equation that I wrote somewhere here, you could think of that this can be thought as this plus 0, and it's a linear circuit, whatever that means. I'm not going to dive deep into it right now, but I want you to think about what do I mean by a linear circuit. You could think of that the response is a summation of response to 0 excitation, superposition of response to 0 excitation, and response to the excitation, which is given by di by dt. And together the new response would you would obtain in terms of V by T, you will get the new response of V by t. But there would be some constants, two constants in this case will come with two time constants because it's a second order differential equation. So its characteristic equations will have two roots. So therefore you will get 2 e to the power minus something, I mean just notionally I am saying, I am not solving right now. You could also have complex roots, so you could have damped sinusoids and so on, but you would basically have two exponentially decaying terms which may come, and the associated constants would be like A and B, but with passage of time their condition, whatever that A and B be, that depends upon the initial conditions at the time of exciting this circuit, but whatever that may be, with passage of time this uh, this terms will go to 0, and then whatever will be left will be a sinusoidal response of the uh, will be basically a sinusoidal response of the circuit, which is described here, so this is what I am going to focus on. I mean, complete response of the circuits you will typically study in circuit analysis course or a network analysis kind of a course elsewhere. In this course we are going to focus on the sinusoidal response of the circuit. So the natural response, we are not taking some funny circuits. The natural response will be damped out due to the dissipative nature of the resistance in the circuit, and after some time you would only see a steady state response corresponding to the sinusoidal excitation function. Okay. Now another very important property of sinusoids which we are discussing at this point of time is that, let's say that suppose you had two whatever this R and L in series, and say this was VR and say this was VL, and let's say that VR was described by A of sine of omega t plus phi 1 and VL of t was described by, let's say, B of sine of omega t plus phi 2. Now when you add or you had two sinusoidal currents flowing through them, and you are calculating the net current, which would then also be something similar to what I am doing here, then the net voltage in this case will be A of sine of omega t plus phi 1 plus B of sine of omega t plus phi 2. Now the point is, what I am trying to say is, and I am going to derive that now, is that when you add two sinusoids at same frequency, they may have different amplitudes and phase shifts, but they are at the same frequency or f or in radians per second omega, then the resulting waveform is also a sinusoid at same frequency. Needless to say, will be scaled, amplitude will be scaled, and there will be phase shift. That is going to happen, but other than that, nothing much is going to happen. So let's write this. Let's expand this A of sine of omega t plus phi 1. This is A sine omega t cos phi 1 plus A sine omega t cos phi 1 plus A sine phi 1 cos of omega t plus sine A cos B plus cos A sin B. Correct? Similarly, B sine of omega t plus phi 2 will be b cos phi 1 sine of omega t plus b sine phi 1 cos of omega t. So when you add these two together, then the v of t is going to be equal to a cos phi 2. I'm sorry, this is phi 2. A cos phi 1 plus b cos phi 2 sine of omega t plus a sine phi 1 plus b sine phi 2 cos of omega t. Correct? So now consider a right angle triangle like this. This is a cos phi 1 plus b cos phi 2. This is a sine phi 1 plus b sine phi 2, and this the resultant C, the resultant C can be given as a cos phi 1 plus b cos phi 2 whole square plus a sine phi 1 plus b sine phi 2 whole square, which is a square cos square phi 1 plus a square sine square phi 1 will be a square of cos square phi 1 plus sine square phi 1, which is a square. B square cos square phi 2 plus b square sine square phi 2 will be b square plus 2ab cos phi 1 phi 2 plus 2ab sine phi 1 phi 2. So plus 2ab cos phi 1 phi 2 plus sine of phi 1 sine of phi 2, which is equal to a square plus b square plus 2ab cos of phi 1 minus phi 2, which is the c square. So it's like saying that it's basically just a parallelogram law of identity, right? Let's say this is my x-axis, horizontal axis. Let's say this is, I think I'll rub this. So let's say this is my phi 1, this is my phi 2, and now you close the parallelogram. Just duplicate this, put it here, change the color to make it more apparent, and let us duplicate this and again change the color, and now let's join this and take a red color. Then it's like saying that if these are two vectors A and B, vectors are shown by magnitude of the first vector is shown by its magnitude of A and an angle of phi 1, and the second vector is shown by magnitude of B and an angle of phi 2, so B and angle of phi 2. Then the summation is going to be, now you look at this is so this is, what is this? This is a cos phi 1, and this being B vector, what is this projection here? Same as this projection, which is B cos phi 1. So therefore from here to here I have got a cos phi 1 plus b cos phi 1, and what is this term here? A sin phi 1. And what is this term here from here? This is nothing but this projection, vertical projection, same vertical projection is here. So you have b sin phi 1. So therefore, what you have essentially drawn here is the same triangle here. This is a cos phi 1 plus b phi sin 1 plus a sin phi 1 plus b sin phi 2. These are phi 2's, b phi 2's, and hence this resultant, the resultant of the parallelogram, is essentially this one, which we just calculated. This is the right angle triangle, and therefore this is the resultant. So the thing is, now what happened to V? And let's call this angle as this third angle here. Let's call this angle as a phi angle. So the V of t now, V of t became equal to C times sine of omega t plus phi, which is to say that when I added two sinusoids at same frequency, I got a new sinusoid with a different amplitude and a different phase shift, but very importantly at the same frequency. And how did I get it? I just got it by doing parallelogram law of identity. So the point is very important point is that sinusoids addition and subtraction of sinusoids can be mimicked by vector addition and subtraction. The new vector is again to be translated as a sinusoid. Translated means interpreted as a sinusoid, but with what is it? Sinusoid with length equal to, or rather the amplitude equal to length of the vector, with amplitude equal to length of vector and angle equal to angle of the resultant vector. Frequency does not change. This is very important. That's the basic reason why we are able to develop the phasor algebra the way we are developing it now for sinusoidal circuits. The frequency does not change. So therefore, whatever I am developing, suppose you had two sinusoids at two different frequencies and then you were trying to do the analysis, then this method of analysis which I am developing, that cannot be applied. This is valid provided in a complex circuit like a all India grid also. If you look at it, even in such a complex circuit like an all India grid, it still requires that there should be only one frequency, which is true. You know, the frequency at Guwahati and frequency at Mumbai of a generator is the same. 50 hertz generator is there. They are same sinusoids at 50 hertz. Maybe different amplitude, maybe different phase angles, but they are actually synchronized, nice synchronized sinusoids. The whole grid from your house all the way up to biggest generator in this country are all synchronized at that same frequency in the steady state. But at every location, you would see that voltages are having different amplitudes and different phase shifts. This is a beautiful thing. You should think about it. How in nature, we are able to do this. It is something just miraculous in my opinion. You need to really ponder over it and think over it a lot to appreciate the beauty behind the electrical engineering, and why it has become so very prevalent in the society, and why the complete society now depends upon it for its survival. Just like it needs air, water, we need electricity, and it all comes down to these sinusoids, differential equations, the responses. I mean, it's amazing. I mean, it just plain amazing. So, so the so 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 to conclude this lecture, I will take this thing again in the next class. But this is, I think, a good point to close this lecture. Two things when we saw. One, when you differentiate a sinusoid, you get a sinusoid at the sinusoid again at the same frequency. Amplitude will change, phase shift will be there, fine, but it is still a sinusoid at the same frequency. And when you add two sinusoids at the same frequency, the resultant is also a sinusoid at the same frequency, and it the resultant could be simply found by representing each sinusoid as a vector, with its uh, amplitude, with its amplitude being the length of the vector, and the argument or the phase angle which comes here, the argument being the angle of the vector. So you can write this as vector A in polar coordinates as vector A angle phi 1. In polar coordinates, the second one is B angle phi 2, and then just do a vector addition using parallelogram law of identities. Then do a vector addition using parallelogram law of identities, and you will get a new resultant vector, whose length is the magnitude of the sinusoid, amplitude of the sinusoid, and whose phase angle is the phase angle of the resultant sinusoid, the addition one. The frequency remains the same. So that's why in this circuit, when so many sinusoids are interacting, because all the generators are generating at the same, exactly at the same frequency, we find that the grid frequency never undergoes any change. It always remains the same, and everywhere you see, if you put oscilloscopes and see waveforms, you will only see sinusoids which are uh, having different amplitudes and phase angles. So if I say phi equal to 0, okay, then what, and amplitude is equal to 1, then what will my waveform be? This. So this is sometimes called as a reference sinusoid. Okay. You could also choose it as cosine of omega t. There is no problem. Any one you can choose while doing a circuit analysis. You can always choose one as a reference. Like for example, here we are choosing x-axis as the reference. You could have chosen y-axis also as a reference, or you could have chosen a reference axis which is at 45 degrees also, no problem. All other magnitudes will remain always the same. Of the length of the vectors don't change by changing the reference axis, but all the phase angles will correspondingly be adjusted, and therefore the difference in the phase angles will always remain the same. So therefore there is no hard and fast rule on what reference one should choose while doing sinusoidal analysis, but usually embedded is a reference waveform which is either often either a sinusoid or a cosinusoid. People choose it by convenience. Okay. If you choose it as, I did everything with choosing sine as the convenient reference phasor. If you do with cosine, then you should think of everything as Vm cos of omega t plus phi. I will write phi v, and for current you should think of, I'm sorry, and for current you should think of everything as Im cos of omega t plus phi of some phase angle I. Now in this kind of a description, the 1 cos omega t is automatically by default the reference waveform or a reference phasor, as I will call it later on. I think that's enough for today. Let's stop here. Thank you.